and welcome to differential equations.
Yay.
That's about 10,000 people in the classroom. The first order of business is to learn what differential equations are and the power of differential equations. And then we'll see how to solve them for the rest of the term. So we start with the definition that differential equation is the equation which contains independent variable, function, and its derivatives. So that's the first definition of the semester. So differential equation is an equation which contains independent variable is usually t, and then f of t, and then f prime of t, might be second derivative, f double prime, and so on. So it contains independent variable, whether it's x or t, the function of that, which also could be called y, and then its derivatives, y prime, y double prime, and so on. We usually write that in this form implicitly: f of t, f of t, f prime of t, f double prime of t, dot, 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 equal to 0. It doesn't have to be equal to 0. We can have something else there, but this is the first thing we do. So that's a differential equation. There are classifications for these differential equations in terms of the terms they have, and also in terms of the derivative that they contain. So you will find second order nonlinear differential equation, which means it's going to have maybe function squared because it's nonlinear. It might have, it will have a second derivative because it was second order, and so on. So there will be those classifications as well that we look into. So let's see. We start with the differential equation, and then we can say classified by order of the derivative. So the highest derivative will tell you whether the equation is first order, so y prime, second order, double y prime, and then third, fourth. You can have any order. Technically, in mathematics, you can go as high as you want. Now, as you are connecting this to application, you start thinking about dimensions. You start thinking about how many derivatives you need to get all the way from position, right, into velocity, acceleration, jerk. So that will be 4 levels. So do we really need more than 4 derivatives? And the answer is no, right? So usually the fourth order would be the highest that we would use. But then, how high can you go? There's no limit to that, right? You can mathematically talk about any order. Then we also have linear versus nonlinear, which means you have the terms to be linear, which is y. It's not going to be squared or anything weird happening with it. It's just y or f of t. But then you might have f of t squared. You might have sine of f of t or y or so on, which would create it as a nonlinear. And that breaks off into a whole different set of equations later on through nonlinear dynamical systems and so on. This is, guys, this is going to cover 10% of 1% of differential equations, whole course. There is a whole bunch of courses afterwards that are going to be extending this and filling in the blanks. We are going to cover the introductory ideas of differential equations that you need to survive your engineering and physics. But then there is much more with DiffEq to learn. Also, there is another classification, homogeneous versus non-homogeneous equations. That's this part being equal to 0 or being equal to a forcing function. We will deal with that classification later. So you have, let's say, a kid on a swing, that would be like a pendulum. It's a simple harmonic motion. There's nothing simple about it because it's nonlinear. There's a sine x in sine t in that thing. But then you might be, so when you have the pendulum, it's going to be damped motion, which means that eventually it's going to stop. So if you put the kid on a swing and you push it, you walk away and you observe it's eventually going to stop. Air resistance and everything else. But then you might be standing behind the kid and constantly pushing. So that's the difference physically between homogeneous and non-homogeneous equations. So if the system is already moving and slowing down and you are not interacting with that system in any way, it's going to be like this. But then if you are there and give the push periodically, sine x, cosine x, whatever, right? Then that would be that function that you are using to force that behavior. So you will see direct links 100% of the time. What we do in this class is we link between the application and the mathematical concept behind. So that classification of homogeneous and non-homogeneous will be introduced later, and then whether the equation is equal to 0 or it's equal to something else, forcing function. So we'll deal with that as well. Now, as I mentioned, differential equations drive 100% of your engineering, 100% of your physics, and all of the formulas are derived from there. And the first example, where I will be introducing also something we call separation of variables, I'm going to introduce a concept of velocity, acceleration, and all of that good stuff that you learned in physics, and just show you the power of this course. So let's talk about position, velocity, and acceleration. Now there is also jerk, which is the derivative of acceleration, how fast acceleration changes. You experience it every time when you push your gas pedal or your brake pedal abruptly, right? If you really slam on those, you have to understand that both your gas pedal and the brake pedal are acceleration pedals. They're changing velocity of the car. So if you are really acting upon those quickly, you experience jerk. That's exactly what it's called. So there is that part, but we're not going to use it here because I'm going to start with the notion that acceleration, let's do the free fall. Acceleration is gravity. So that negative 32.2 feet per second or 9.81 meter per second or per second squared. Gravity, and we can put the negative symbol there, right? Because gravity goes down, pulls downwards in our frame of reference. And now we define the acceleration as the change of velocity, right? Acceleration is change in velocity, and that happens in time. You can't instantly change velocity. It goes over time. So I'm going to say that acceleration is the change of velocity in time, and that is equal to that negative g. Now this part over here in the red box is actually first order linear differential equation, and we're also going to put in the word separable because it's very easy to solve. So first order linear differential equation right there. We solve this by using separation of variables. And this is the method you already learned in your calculus class, so this is technically a review. This means that all of the variables should be separated on if possible, on other opposite signs of the equal sign. So you have V's and T's. G is a constant, right? So that's not a variable. Well, g is a parameter, not a constant. It's a parameter because it's going to be different for Mars and different for Moon, right? As a concept, gravity is, but even on planet Earth, it's not constant because at the top of the mountain and the bottom of the valley is different values. All right, so we call those parameters. They're not variables because gravity can take any value. It's a parameter, a specific value for specific locations. But it acts as a constant. So g is a parameter, as a constant. You can just drag it around. It's not a variable, where t and v are variables. So now we are separating variables by saying that the dv is equal to negative g dt. I move dt to the other side. And how do we solve this? Who remembers Calc 2? Integrate both sides. Very good. So I will hit integral signs on both sides. We have the integral of dv is just going to be v. Negative g, you copy that, and integral of dt is t plus some constant c. Now you might be avoiding that plus c in your calculus courses because, right? But now this c is crucial. Every time you forget c is going to be devastating for the problem. So you have to get into that notion and habit of putting plus c every time you integrate. Now you're looking at this formula and you're trying to figure out what is this. Well, this c is actually your initial velocity. Usually called v0 in your physics courses. And now, if you look at your formula, you will have that the velocity in terms of time is v0 minus, well, let's start with minus gt. Negative gt plus v0. Now in physics, you write v final is equal to v initial plus acceleration times time. You see that? So we retrieve that formula like this, using differential equation. And now we say that the velocity is changing position. In order for me to be going, I don't know, 10 miles per hour, well, that means that if I start at point A, in 1 hour I'll be 10 miles away. So position, right? We have now position. So velocity is changing position. So this is one of the good equations. Velocity is changing position. Variable for position is s, clearly, right? Because position, right? There is s in it. S, position. Right? So there's that. And that's equal to negative gt plus v0. Again, we have a linear first order differential equation. Separate variables. And we are going to get that the ds is equal to open parenthesis negative gt plus v0 times dt. And we integrate both sides. So now s of t is equal to negative 1/2 gt squared. Remember that the integral of t is t squared over 2, right? We all good on that? Plus v0t plus c, some constant. Now in this case, c is initial position. In this case, height, if we are doing free fall, because negative g, right? So we have that s of t is equal to negative 1/2 gt squared plus v0t plus s0, and this is exactly the equation that you learned in physics for your parabolic motion, right? And you actually see that all of the important aspects, physical aspects, are there, right? You have your gravity term, which pulls it down. You have your initial velocity because you either threw something with initial velocity or you dropped it when velocity is 0. And you have the height from which you are thrown, right? It's not the same whether you throw the baseball from 6 feet height or 3 feet height, right? So that's why the baseball players are not 3 foot tall, because the ones that are 6 foot tall are going to throw it further, right? So this was a demonstration on how the position, velocity, and acceleration are related through calculus, but it's differential equations that take you from acceleration all the way back to position. Now, if you have a position function, you differentiate, you get velocity, you differentiate again, you get acceleration, differentiate again, you get curve. And all of those are formulas that you can use to find where the particle is, where the car is, what the velocity of the particle is, and so on. So you can find locations, velocities, and so on. Very important in your engineering design. Would you argue that SpaceX uses some of this stuff? Yeah, all of the engineers look like you guys. Yeah, you see the videos? They're all like 12. But they launch rockets in space. Have a great time. Let's talk more application. This lecture is about importance of differential equations and connection of these to our engineering and everyday experiences. Biology. We're talking about population models. Another one that you already did before is it says that change in population is proportional to population. That's technically what it is. So change in population is proportional to, I struggle to put this in one line because now I want to write differential equations. I want to translate this sentence directly into differential equations. Change in population dp dt is equals proportional k constant to population p. There you go. dp over dt is equal to kp. This is the simplest possible differential equation that you can write for population. It's accurate for short period of time. Overall, it's bad, but on a short burst, it's good. So now we have the differential equation that has dp over dt is equal to k. P, again, separate variables. And we're going to get dp over p is equal to k dt. And we hit it with the integral on both sides. What is the integral on the left? Anyone? ln. ln absolute p equals to, and on the right hand side, kt. Yes, plus c. If you don't have this in this course, you are doomed. And I'm not saying doomed with 2 O's. I'm saying doomed with like 6 O's or 7 O's. Doomed. Plus c. I need to fish out p. So exponentiate both sides. So now p is equal to e to the kt plus c using algebra, e to the kt times e to the c. This new constant, I'm going to call it p0, initial population. So p of t is equal to p0 e to the kt. Population model. Now, we like to see if this model makes sense. In order for population to change, you have to start with population. P0 has to be a non-zero number. You can't get the population without having population there already. So if you start with 500 rabbits, depending on this k, 500 rabbits are going to go up in population or down in population. Now, that k is the growth or decay rate. And we have to understand that that k is going to take a look at a lot of factors. It is not something that you say, all right, it's just a growth. You have to understand that that k also reflects what type of population you have. If you have 500 male rabbits, population going to change? No. Yeah. K is 0. Well, actually, no. Over time, yeah, they will die, sure. But if you have 500 immortal male rabbits.
Can I have one?
No, they're vicious. Because they don't care. Immortal. I have no idea what they want. I've seen an immortal rabbit like strangle people. So if you have a population of 500 immortal male rabbits, K is 0. K is 0. Because they're not going to multiply. Can't adopt either. Rabbits have no form. And in that case, K is 0. If you have, let's say you have 250 male and 250 female rabbits, K is going to be high. Let's say I have perfect match 1-for-1, whatever, right? But the idea is that it's not just a number. It's actually a number that describes this. We'll see this coming back again when we do Newton's law of cooling in like 17 seconds. But before we go on with this, I want also to mention that you can't use every model you get from differential equations blindly in any situation. We know that the population on Earth is growing. It's growing pretty fast. We have 7.4 billion people right now. Some studies point towards 10 billion being a cap that planet can sustain. Now, for k larger than 0, how does the graph look like on this one? It's exponential growth like this, with this being P0 and this being T. What's happening with population? Yeah, the limit of this. This is why I need to know limits. So the limit of P of T as T goes to infinity is infinity. And we know that this planet cannot sustain infinite amount of people or rabbits. So there are food, right? Food resources, energy resources, and all of that stuff, right? Space, right? Just where to live. So we know that this is overall bad population model. But it's good on a short run. If I take the numbers from 1980 to 1990 and I want to know what's happening in 2020, should be good enough, right? But I can't really go into year 3007 because it's going to be really off, really off. So to fix these things, you would add more terms to this sentence. And you will not just say that change in population is proportional to population, because it's not. There's more. Energy, wars, AIDS, right? All of that stuff plays the factor in writing. And you have to keep subtracting terms. So it's proportional to population, but then minus this death, and minus this tragedy, and minus that, right? And so on. And then the differential equation changes, and it becomes much harder to solve, but the equation you get at the end, which is mathematical model, is much better for the population. So when you're watching and looking at online on that website, world clock or whatever it is, population clock or whatever it's called, and see that ticking, it's not this differential equation behind it. Something far more complicated than that, right? So that's that part. So that was the part on population. Let's see what else we can talk about. Well, you had enough already? Damn. What else can we talk about? Newton's law of cooling, which is also Newton's law of heating. All right? So you either cool or heat something over time. The change in temperature of the object is proportional to the difference between the temperature of the room and the temperature of the object. So if you have a hot coffee on the table, the coffee is going to heat up the air around itself, but all of the air around it's going to cool the coffee. So there is exchange in heat between the two. The increase in the overall temperature of the room because of the cup of coffee is going to be insignificant in comparison to how much the coffee is going to cool down. Just because of the volume, sheer volume of the coffee towards the room. You probably heard action-reaction, right? Every time you jump, right, and you land on the earth pushes on you and you push on the earth, right? Well, yeah, you actually move the earth every time you do that. But it's so insignificant in comparison to what earth does to you, because earth is just so much bigger. So that's that part. So when you have a cup of coffee, or you're thawing something to eat later, right? The room, which is much, much bigger than the object that you are cooling down, is going to get heated up. But the thing that you are cooling down will cool down or heat up, depending on what you're doing. Newton's law of cooling. So there's no way I can fit this in one line. I mean, I could, but it's just going to be weird when you print it. So the change in temperature is proportional to the difference between temperature and environment. I tested this. I made a Thanksgiving turkey using this principle. Calculated that I needed exactly 3 hours, 15 minutes, and whatever number of seconds I can actually look up. And it works like a charm. So change in temperature in time is proportional to the difference of temperature and the room temperature. Our book is using A, whatever you come up with. So there it is. The change in temperature in time is proportional to the temperature and so on. Now, book is placing there a negative sign. I'm not going to put the negative sign on K because cooling is going to be positive K and heating up is going to be negative K. And book is fixing that by introducing the minus sign there. This is another separable differential equation where you go and you say dt over t minus r is equal to k dt, and you do the same magic of integrating everything and working it out. So I'm just going to put 3 dots there because it's the same stuff over and over and over again. And you got to use the u sub here, so whatever. Torricelli's law says time rate of change of volume V of water in a draining tank is proportional to the square root of the depth of the water in a tank. Another one. And you have many of these examples, but it's enough. So every single one of these examples says the same thing. There are words. You read those words. If they have the rate of change in them, it's going to be differential equation. You write that differential equation down, and then the rest of the book is how do we solve them. Now, much of this will be focusing on techniques of solving differential equations rather than application of them. But you will have a lot of application in your engineering courses. Did anyone take circuits yet? Poor soul. How was it with the systems of differential equations when you did AC circuits? It was okay. But you did systems of second order differential equations before you actually learn differential equations, right? But yeah, it will make sense by the end of the class because we'll do those here. So circuits analysis is a course that eventually you might take, and in that course you guys will see systems of differential equations. Just like you have systems of regular equations that you are used to, like 2 variables and 3 variables and so on, you'll have the ones in circuits. And you solve those in a particular, we'll learn 2 or 3 different methods of how to solve them in class. So you are going to have a lot of application of these, if you can figure out where they fit, in your coursework when you take engineering classes later on. So we'll be focusing not that much, unfortunately, on applied problems. We'll have at least 3 or 4 sections that will be just applications. Like this one was application. We'll see how to translate all of the physical properties. But we'll be mainly talking about solving differential equations. And those differential equations will be boring in terms of here is the y double prime plus 3y prime plus 10y is equal to sine x, and then sine t, and then let's solve that, right? Without connection to the world. But then some of you might say, well, where does this actually fit? And I say, oh, the spring mass problems, they look exactly like that. And then you would say, okay. So we are going to connect these things, but it's not going to be application-driven course, unfortunately. What else is there? So we talked about linear versus nonlinear. So if you see a sine of y, y squared, so nonlinear terms, then equation becomes nonlinear differential equation. Some of them easy to solve, some of them absolute nightmare. Depending on the case by case, we'll deal with that. We also have extensions of this. I already mentioned dynamical systems later on. One course that follows this necessarily is called partial differential equations. Differential equations is focused on the derivative that you know and love from Calc 1. Derivative of x squared is 2x, right? But how about the partial derivatives from Calc 3? that gives a completely new branch of differential equations called partial differential equations. Now those are solved mainly in power series. Much scarier than what we have here. Professor Kovarik and I like to give these off lectures in math. So we had a discussion already about offering complex variables and partial differential equations this semester, which will be a series of 3 to 5 lectures. And if you guys are interested in that, you will let me know. I'm inviting half twos, threes, and differential equations, and tutors. So if you guys have interest, we'll compile the amount, if we have about 10, 15 people, we'll give these lectures. They're usually about an hour and a half a day. Right after this, in the evening, sometimes, let's say 7 or 8, and only 5 classes or so. You will get exposed to some of that later mathematical work that will, if you want to study thermodynamics or something serious at the 4 year, you gotta know those partial differential equations, because forget about it. You can't do anything without them. So partial differential equations will spin off of the partial derivatives, and you have that. So wave equation, heat equation, and all of these equations later on are introduced, not in this course, are partial differential equations. And that's the part. Now, there is a lack of understanding of what the differential equations are, a little disconnect, so that's what I'm going to still add to this 1-1 part, that if you don't understand, it's going to be a really big problem. So I'm going to start by making something clear. Let's first solve the regular equation that you all know and understand, hopefully. X plus 2 is equal to 5. This is called an equation. You studied this about 15 years ago, and you know how to solve this. How do you solve this? What do you use? Does anyone know mathematical terminology of what you have to use? Nope. It's called additive inverse. You will add -2 to both sides. You know the process, you just don't know the name. And you get x equals to 3. Terribly exciting. And then you're going to check this, because you're still not sure. See how exciting this is? It's breaking the classroom. You say 3 plus 2 is equal to 5, and then 5 is equal to 5, right? So you check. Now there is a completely parallel world, much more powerful than this method, that runs on the side. And it's called graphical solution to this. Any equation that you can solve this way, and those that you can't solve this way, can be solved graphically. I'll explain what I mean, but let me just solve this equation first. So on the left-hand side, let's go like this. In the blue corner, we have a linear equation y equals x plus 2. Y-intercept of 2, slope is 1. It is a 45-degree line that will go forever, and this is your x plus 2 equation. On the right-hand side, you have, in the red corner, you have 5. Y equals 5 is the horizontal line that goes through 5, like this. Where do they intersect? Where do they intersect? They intersect at the point 3, 5. You see how x is equal to 3? In all of mathematics, you don't have to know any method of solving equations at all. None of them. Not trigonometric, not exponential, logarithmic, this nonsense, nothing. If you know how to graph, and if they intersect, there's your x. Every time, no exception. Mathematics. So in this, I want to bring three concepts together. A concept of solving equation, what we say algebraically or analytically. Shuffling those x's around, or these, or whatever. Graphical solution to the same thing. And check. Some students will say differential equations is such an awesome course because it's equations. You get the solution, you plug it back. If it doesn't work, it's wrong. Right? What do? You redo the thing. And you keep doing it that way until you get it right. Also, we are going to learn, I believe next class, slope fields. That equivalent to this. You solve every equation graphically, and you just don't need to open the book at all. We don't need any of the next 14 weeks of material. And that's where the numerical part come in. You also have to understand that there are equations that contain x's from your previous education that cannot be solved by hand. Take a look at, let's say you have e to the x equals to x plus 3. You can just cry about it. You can't solve it. There's no way. So e to the x is equal to x plus 3. This can't be solved. How do you get rid of e? Yeah. So you want to free up this x, right? So you ln both sides. Ln is going to kill e. You get x equals ln x plus 3. All right, so you freed x on the left, but now you trapped the one on the right. Now, how do you get rid of the ln? Oh, you e both sides. Great. So now e both sides, and you get e to the x plus, yeah. And you see how wonderful this gets, right? And then before you start pulling the hair, right, you have to understand it cannot be solved analytically. The only way to solve this problem is to graph it, and if they intersect, those are your solutions. So you know that the graph on the left is exponential function that goes through 1. And on the right, you have a linear that goes through 3. And there they are. I don't know what they are. I can find them numerically. But x1 and x2 are the solutions to this equation. I know for a fact there are 2 of them. There's no way in hell there's less or more or something like that, because that's how the graph looks like. Now this is the only way to solve this. No other way. That's it. Well, there is another way. Right? This is a power series, add this to the other side, solve it to 0, find the roots. Good luck with that. It's like 5,000 words, 5,000 times worth of this. But power series solve all your problems. But we're not there yet. So now you see an equation that was like this to solve, and you see the one that you cannot solve at all. Right? Both of them easily solved by graphing. Now that brings me to differential equations and their solutions. We're going to have 1 solution, 2 solutions, 3 solutions, depending on the order of differential equation, the type of differential equation, and all of that stuff. Now I want to go and write this terminology so that we are all on the same page from day 1. And that is dp over dt equals to kp is called differential equation. P equals P0 e to the kt is called solution to the differential equation. There's more to it. It's actually general solution, but there is particular. Well, we'll talk about that. And now, here's the $1 million thing. Check. It is equation, which means you can plug stuff in. If it equals and works, your equation is 100%. This is why on every exam you can literally walk to the desk after the test and just say put the 100. There's no need for me to read it. Because if you take the derivatives, plug everything in, and everything works out, it's a definite 100 without thinking. If you don't do that, then you're going to sweat until I bring it back and then see, then you say, oh, really? I got this much, and then I have to regrade it. So how do we check? You have the solution. How did you check here? You plug it back in, right? So there's no difference. Just plug back. You have what P is. It's all this stuff. The hell just happened? Yeah, this was really plugged in now. Like it really plugged it in for all eternity. There we go. It's Microsoft trolling me for. So clearly, I need to plug in the derivative of P over here and P itself over here. So you just replace them. That's all it is. From here, what's the derivative? P prime. What is it? It's P0, and then the derivative of e to the kt is k e to the kt. That's what the derivative is. So now, plug in everything. dp dt equals k p. Instead of dp dt, I have p0 k e to the kt, and on the other side I have k, and instead of p, I have p0 e to the kt. You see how they're the same? We know that a times b is the same as b times a, right? Community rule. They're the same. This is what you're going to encounter in every single problem. Now, some of those solutions are going to be very long, and it's going to take time to take the derivative, maybe involve the product rule, and so on. Right? Curse on the side and just do it. Plug everything back in. When it checks out, you know you have the correct solution. That's great. If you never develop that intuition from your integration, how do you check integrals? You do it, yeah, take the derivative. If we get the same thing you started with, the integration is correct. If you get something else, it's wrong. So that's why, in my case, my first half of Calc 2 was like 150 out of 100, right? And then the partial, then the series 15. How is going on over here? Still right, great. So the same thing goes for the differential equations, guys. You will get the solution, and if you're interested in your progress, you will take the derivative, plug it in, it checks out, it's 100. If it doesn't check out, it's like 30. You decide whether you want to fix it or not. That's enough for today. That's called efficiency. We went over the syllabus. We went over 1.1. Now we're going to talk about homework. I'm going to end this stream. And, if it's good, we'll continue streaming. We'll see how it works. I hope this stream still works. Yeah, it's live. Hey, it's yellow. It's okay. Bye, stream.